Hello everybody and welcome to page 18 of the workbook. And this is the second half of section 5.5, the idea of integration using tables. Okay, so just kind of a word about the direction that we're going to head in here. We've talked about a variety of different integration techniques up to this point. And we've discovered that some of them are pretty long, like partial fractions. That's a lot of work to do an integral that way. And so what mathematicians and engineers and scientists have noticed through the years is that there are a lot of functions that tend to come up over and over again that you see in integration problems. So it would be nice to not have to redo the same problem over and over and over again. And so what they compiled is a list of integration tables that we can use to just do integrals more quickly. Okay, so what I'm about to show you here is the table of integrals that we're going to be using. Okay, and it's a big, long list of formulas, okay, of integrals. And when you first look at it, it might look kind of overwhelming. There's just a lot of stuff on here. Okay, but as we do some problems, you'll start to see that there are some patterns. There are some ways to kind of navigate your way through this table and find the integral that you're looking for. Okay, so with that in mind, let's go back and take a look at an example, example 4. This is going to be our first example illustrating how we might use this integral table. Okay, so here's what they'd like us to do. They want us to complete the square and use a substitution to evaluate the integral of 1 over x squared plus 6x plus 13. Okay, so let's start with completing the square. And they're actually just talking about the denominator here. All right, so I'm going to take the denominator, x squared plus 6x plus 13, and we'll review the process of completing the square. The idea is we'd like to take those first two terms, I'm going to leave a little space, and think about, is there a number that we could add, okay, right here, that would turn the first two terms into a perfect square? And it turns out there's kind of a technique for figuring out what that magic number is. It involves looking at the number that's in front of the x, the plus 6, and doing two things to it. We're going to take that number, we're going to divide it by 2, and we're going to square it. 6 over 2 is 3 squared, which would give us 9. Okay, and so it turns out then that 9 is the magic number here. Okay, let me fix that. Okay. So what we want to do is to add a 9, but if we just added a 9 to this equation would not be true anymore because we added 9 to the right-hand side without doing anything to the left. So to compensate, we're going to subtract the 9 again over there. So now the equation is balanced because we added a 9 and subtracted a 9. Okay, and the reason for doing that is those first three terms, the x squared plus 6x plus 9, that is something that's factorable now. It factors as x plus 3 all squared. Okay, and then we come to the second piece, 13 minus 9. If you subtract those, you just get a 4. So what we've redone is just rewritten our denominator as x plus 3 squared plus 4. All right, so here's what we can do with that now. If we go back to the integral that we're trying to calculate, we now know that the denominator can be rewritten as 1 over x plus 3 squared plus 4. And notice that that suggests a possible u substitution that we could do. We could let u be x plus 3. Okay, and if we do that, let's see. The derivative of x plus 3 is 1, so du is going to be dx. And if we complete the substitution, let's see, that's going to give us 1 over u squared plus 4 du. Okay, now what we're hoping is that by doing all of that, completing the square and doing the substitution, the new integral that we have might be something that we can find in our integral table. Okay, so let's take a look. So remember, 1 over u squared plus 4, that's what we're looking at. Okay, and if you look down the table, we're going to kind of get lucky in this case that we have something that matches pretty well in the first block of formulas, number 17 here. Du over a squared plus u squared, that's the same function that we're trying to integrate if we let a equal 2. Okay, because if we let a equal 2, we're going to get du over 4 plus u squared. That's exactly the function that we're integrating. Okay, and the table tells us that the antiderivative looks like this. 1 over a arctangent of u over a. So I'm going to go back to the previous page and just write down that antiderivative, but everywhere I see an a, I'm going to write a 2. Okay? So we're going to get 1 over 2 arctangent of u over 2 plus c. And just to remind you where that came from formula number 17 in the integral table. Okay, and then finally, last step to finish this, we just need to substitute in what u was equal to. And that's sitting up here, u is x plus 3. So our antiderivative looks like 1/2 arctangent of x plus 3 over 2 plus c. Okay, so just one general comment before we close this example. This illustrates the idea that to use the integral table, usually, or very often anyway, we have to take our function and do something to it. Maybe do some algebra, maybe do a u substitution, so that we can get it into a form where we can recognize it as one of the formulas in the integral table. You'll see that the examples that we do after this kind of follow that same general pattern.